Chapter 1. It's kind of your general overview to make you excited about science. And maybe sort of make you optimistic, but we'll see. So why science? If you're a pessimist, you look at this picture, what do you see? Any ideas? Do we have any pessimists in here? Doesn't have what?
So it doesn't have a crust over the top. That's what you want.
Okay, no crust. Okay. Did you say no strawberries?
A lot of strawberries.
Oh, a lot of strawberries. That's a pessimist?
No.
Too many.
I thought that was pretty good. Maybe you go with too many strawberries. I'm just going to say straw.
Really sweet.
Calories. Too sweet. We come up with all things. No whipped cream. I mean, God, that's awful. Right? So we've got all these nasty things that a pessimist could look at. Optimist looks at it and says,
It's pretty.
pretty. That's reasonable. I like that one.
It's messy.
The crust is even.
3 pie. Okay.
It's messy.
Messy is an optimist? I like that. It's a good optimist thing to think about.
Healthy because it has fruit in it? I
Ooh, there's an interesting idea. Healthy. That is a really optimistic thing to be saying there, but we can run with that.
Or for the pessimists, it's bad for people who have diverticulosis.
I can't even spell that.
don't know. People that have diabetes also.
I don't have it, but
There we go. Die something or other. Okay. What does a scientist look at it and see?
It's a pie.
See a circle?
A shape.
Look at
The
shapes.
number.
Symmetry.
it's a conglomerate.
Switch to a chemist. What does a chemist see?
The chem.
I can make that better. Okay. That's what a chemist sees. They don't look at it and say all these different shapes or how it tastes or what it looks like. They say, I can do better. Okay. Is it egotistical? Absolutely. But that's what our scientists are. They're egomaniacs that are pointed solely towards making something better. Okay? That's what chemistry was there for. I want to make something better, cheaper, faster. So they can go through and they can break this down into the individual components. You used white bleached flour. That's not healthy. I'm going to add some whole wheat flour into that crust. You use pesticide-covered strawberries. I'm going to make them organic strawberries. Okay? I'm going to scrub them by hand with purified water. Okay? That's what a scientist goes back and does. Says, I can do better than what's already established. Okay? That's what we're trying to do with science. Okay? Bit of a stretch, but that's kind of our goal. Which then gets us to this scientific method. Okay? So we're trying to learn something new, trying to make something better. That's our goal. So what we'll do is make observations. So what could we make for the observations on that pie? We could look at color. Okay, I can make that better, or I can sell it for more if I color it redder. Then people go, that looks tastier because it's more red, and they pay more money for it. Okay, that's marketing, but beside the point. Okay? So we can come up with different observations of it. We could change the color. We could look at what ingredients made it up. Flour, strawberry, sugar. Where'd the sugar come from? Was it just the white junk sugar, or did you use demerara sugar? Okay, did you use fancier sources? Did you use molasses? That might be a little weird, but okay. So we make those initial observations, and then we come up with a hypothesis. I can make that better by switching from white granulated sugar to demerara sugar. It's got more flavor. It's got more kick to it. Okay. What do we do once we have that hypothesis? We test it. We go to experiment. Okay. And this is where I think our textbook and most teaching classes have ultimately been disingenuous to students. What happens now? In your analysis, you find your experiment failed. Okay? I decided instead of using white granulated sugar, I wanted to use molasses. That's probably going to taste awful. Okay, I could be wrong on that. I haven't made a strawberry pie with molasses. Okay, but it's probably not a good combination. So that's now failed. So I go back to my hypothesis. Say, well, molasses was a bad choice. So I'm going to switch to a different type of sugar, maybe a different source of strawberries. And then I go back to my experiment and I test it. And what happens? You fail again. So you go back to the hypothesis. Change your hypothesis again. Go back to the experiment. What happens? You fail again. Okay. This cycle sits in this failure experiment hypothesis again and again and again and again and again, and it very rarely ever moves on. Okay? Maybe 1% of the time do we actually get a success out of our science. Remember, 800 years. That's a long time that we spent failing. And in that failure, okay, we're condensed it down to 16 weeks. That's a whole lot of other weeks that it didn't work. Okay? So you will fail. Okay? But that's where science becomes amazing. Because scientists accept that failure and they go back and they try again. And they try again. And they try again until they succeed, until they move forward. Okay? And that's where we end up with our scientific theories or our natural laws. What becomes fun after you've failed all that time and you make it down to these theories and laws? You've now spent all that time and all that research and you've now come up with some new law or theory. Then guess what do? Remember, you're an egomaniacal blah, blah, blah.
Name it after yourself.
Yeah, name it after yourself. Okay? Highly frustrating for you because now what do you have to do? Not only do you have to understand the theory, but you now have to tie someone's name to that theory. Okay? So names do pop up every so often. When it comes to the history of things, I do tend to tie names into different theories and important discoveries. But I do try and keep those limited to only looking at our atomic theory. Okay? All science sits in that failure setup. Okay? You talk to any of the famous scientists, that's what they reference. Okay? Everybody comes, oh, how'd you think up that theory? That was amazing. How'd you do that? And you go, oh, I spent 50 years failing at that theory. I just did it once. Okay? If they're really honest, they actually point that out. If they're not honest, they go, yeah, of course, I'm awesome. Thanks. Okay? But the honest ones go through and tell you that they failed. Okay? They spent time working on those experiments. Chemistry's role. Every time I edit this slide, it goes to change it again. All right, we've got mathematics and physics, kind of our hardcore sciences on one side. And on the other side of that bridge, we've got biology and other stuff. You can see where my emphasis lies. Biology is kind of your larger aspects. We don't get into the nitty-gritty details. Whereas our mathematics and physics looks at the hardcore numbers, how things shift, move, all those rules and laws about all that fun stuff. How do we connect mathematics and physics to biology? That's what chemistry is doing. Chemistry is bridging that gap, bringing those two fields of knowledge into one general location so that we can kind of smooth the transition from the hardcore physics and mathematics, which is beautiful to watch someone do, but you have to be good at it. I'm not one of those people. Okay? Which then gets us to the field of our general chemistry. What you're learning is general chemistry. Is that the only chemistry? No. There's organic chemistry. There's biochemistry. There's inorganic chemistry. There's physical chemistry. All of these different branches of chemistry. What are you trying to learn in this class? All of them. Ta-da. Okay. Not particularly pleasant for you to deal with, but realize that's what we're really trying to do. Is we're trying to give you this big superficial overview of everything within chemistry. How are you going to ever become a master at any of those subjects?
You have to have a foundation.
You have to have a foundation. Where do you get that foundation?
General.
From more classes.
Oh, yeah.
Okay? Really all we're doing is giving you a quick overview so that the terms don't look foreign to you when you move into another class. Okay? If you're not moving into another chemistry class, we're hoping that when you then go out into the world, you look at those terms and they don't look foreign to you. You have some context on what they mean. So when someone refers to dihydrogen monoxide, you don't freak out. Oh my God, that's a big chemistry name. What is dihydrogen monoxide?
Water.
Water. Okay, it is pretty dangerous. I mean, you can drown. Okay? But it's that interpretation of this big nebulous system that we want you to kind of have some foundation in when you leave this class. When you move into other classes, that's when you learn more about those individual details. Kind of make sense? Okay, should I keep going? It's fun having the clock behind you and not in front of you. So we're actually done. So I'll stop.